All right, so one of the gas laws you'll see in class is going to be Gay-Lussac's law. And Gay-Lussac actually described the relationship between pressure and temperature when the volume remained constant. So let's actually look at this ourselves. So we have a container here, and it's a 5-liter container and inside has gas particles. Okay, so it's at room temperature, and the gas particles are hitting it at some sort of pressure. And that's fine. Let's say we heat it up, so we're increasing the temperature, and the kinetic energy of the particles within the 5-liter container is increasing as well. And they're hitting the sides of the container at high speeds. And so what's going to happen, as long as the volume remains constant, which it is, the pressure inside the container is going to increase dramatically depending on how much the temperature is increasing. So let's talk about this relationship. We know it's a direct relationship. As temperature increases, so does pressure. And conversely, as temperature decreases, so does pressure. So temperature and pressure have a good relationship as long as the volume remains constant. Okay, so let's put this in mathematical formula. Pressure 1 over temperature 1 equals a pressure 2 over temperature 2. Because this is a direct relationship, they are divided by each other. The temperature, we're going to make sure is in Kelvin. And the reason we make sure it's in Kelvin is because we want to make sure that there's no negative numbers on the denominator. And Kelvin's the only temperature scale that actually only has positive numbers. So we're going to make sure this is in Kelvin. And this is Gay-Lussac's law mathematically. Graphically, if we put temperature on the x-axis and pressure on the y-axis, we know that as we increase temperature, we also will increase pressure, creating a positive slope. Okay, let's actually look at this in a demonstration. So what I have right here, I'm going to put my goggles on, make sure we are safe. Safety comes first. We have what I'm having on this hot plate is a Coke can, as you can see, and I'm heating it up. So the gas particles inside the container are heating up also, and they're hitting the pressure of the soda can at high speeds. But it actually is open, so it has a place to escape, so the pressure inside the container is equal to the pressure outside here, and so everything's all good. But what I'm going to do is I'm going to flipping the can over into this ice water bath, sealing the container. And what's going to happen is the temperature is going to drop, and so the pressure inside the container is also going to drop. But the pressure outside is going to remain the same. So what is going to happen? Let's see. Whew. So, as you can see, it actually didn't take much at all. What happened was the pressure outside was so much greater than the pressure inside because we had dropped the temperature so dramatically that it actually pushed on the can and crushed it, as you can see, completely crushed it. Okay, don't try that at home. All right, let's turn this off, and let's go and solve a problem together. Okay, so if the pressure in a car tire is 1.88 atmospheres, there's our first pressure. At 25 degrees Celsius, there's our first temperature. What will be the pressure if the temperature warms up to 37 degrees Celsius? Okay, so first I want to make sure these temperatures are in Kelvin, not in Celsius. So I'm going to change them. 25 degrees Celsius plus 273 is equal to 298 Kelvin. 37 degrees Celsius, that should be a degree Celsius, plus 273 is equal to 310 Kelvin. Okay, so my first pressure, and when I woke up, I put the tire pressure was 1.88 atmospheres. And the temperature outside was 298 Kelvin. We don't know, we went into the pressure at the end of the day when it's 37 degrees Celsius. We don't know it, so we're going to say X over 310 Kelvin. We cross multiply 1.88 times 310 divided by 298, and it's going to give me 1.96 atmospheres. So the pressure inside the tire is actually going to increase as expected because temperature also increased. So this is an example of Gay-Lussac's law in an everyday application.